Welcome to this second lecture on the physics of magnetic resonance imaging. In this lecture I will primarily explain the principles of MR image formation and describe the spin echo and gradient echo pulse sequences. MRI was originally called by the more accurately termed nuclear magnetic resonance imaging, but with the negative connotations of the word nuclear, although MRI has nothing to do with radioactivity, that was soon dropped. The Nobel Prize in Physiology or Medicine was awarded in 2003 jointly between Paul Lauterbur of the State University of New York and Professor Sir Peter Mansfield from the University of Nottingham for their discoveries concerning magnetic resonance imaging. The crucial invention as far as imaging is concerned was made by Lauterbur, who apparently had the idea whilst eating a hamburger. His great idea was to introduce the concept of a magnetic field gradient for spatial localization. He called his technique zoigmatography, from the Greek zoigma, to join. Fortunately, that name did not catch on. The magnetic field gradients are superimposed on the static magnetic field B0. Gradient pulses are typically drawn as trapezoidal shapes. We start with the gradient taking a finite period of time to reach the desired amplitude, which is then held for a duration known as the plateau, before another period of time for the gradient to switch off. The animation shows a very early gradient coil, which has been withdrawn from the center of the magnet. I have superimposed a gradient in the Z direction being switched on, held for a brief period of time, and then switched off. The fulcrum of the gradient is in the middle of the gradient coil assembly, which would normally be at the isocenter of the magnet. One metric used to describe gradient performance is the slew rate, which is the maximum possible gradient amplitude, Gmax, divided by the minimum time it takes to reach that amplitude. For example, if the maximum gradient amplitude is 50 millitesla per meter, and it takes 250 microseconds to reach that amplitude, then the gradient will be said to have a slew rate of 200 Tesla per meter per second. The important concept regarding gradients in MRI is that for MRI to still work, the spatial variations in X, Y and Z also require the gradient magnetic field to be always pointing along the Z axis. In this case of the X gradient, we have the gradient coils which are arranged in what is called a quadrupolar or Golay configuration. The currents are circulating through this gradient coil to make this a north pole and this a south pole. We will then have a strong magnetic field from north to south, nearest the surface of the gradient coil assembly, and then decreasing linearly towards the center of the coil arrangement. This magnetic field will add to B0. The gradient will be 0 at the isocenter, and then because of the opposite polarity arrangement on the other side of the assembly, the gradient amplitude will again increase linearly, but in the opposite direction, subtracting from B0. In the Y direction, we have the same quadrupolar arrangement, but just rotated 90 degrees, so that now the gradient is going from the top to the bottom of the gradient coil. The Z gradient is a little bit simpler. We have a Maxwell pair in which there are counter-rotating currents. The effect of each gradient is to create a spatially dependent variation of the Larmor frequency with position. For example, in the Z direction, there is a continuous linear decrease in Larmor frequency from the north pole of the gradient to the isocenter, where the Larmor frequency is just given by the static magnetic field, and then a further decrease in Larmor frequency towards the south pole as the gradient is in the opposite direction to B0. Here we have a subject lying inside the magnet with the main magnetic field pointing from their feet to their head. If we look at the protons processing at 3 different locations, ignoring any non-uniformity in the static magnetic field, we can see that at all 3 Z locations, the protons are all processing at the same frequency. If we now introduce a Z gradient using our Maxwell pair coils, we can see that the proton in the center is still processing at the Larmor frequency, gamma times B0, but the proton to the left is processing slightly slower, and the proton on the right is processing slightly faster due to the presence of the gradient. Here is an audio frequency analogy to try and make this a bit clearer. On the left, the proton with the highest precessional frequency can be represented as a high frequency note. The proton in the middle has a slightly lower frequency, and the proton on the right has the lowest frequency. However, the signal that we detect from the patient will be a mix of all three frequencies. So we have no positional information. The question is, how can we deconstruct this mix of frequencies into its individual components? The answer is, of course, with a Fourier transform. If we Fourier transform the combined signal, then we will get three resonant frequencies. And if we know the strength of the gradient accurately, Gz, then we can translate these frequencies to positions. In reality, we will have a continuous distribution of frequencies, and the Fourier transform will give us a one-dimensional projection through the patient. This is a typical echo signal that you could receive from the patient. If we show this as a line of raw data in a false color, it will look like this. And if we acquire all the necessary gradient steps to obtain an image, then the full array of raw data will look like this. This raw data matrix is often called K-space for reasons we will discuss in a moment. By simply applying a two-dimensional inverse Fourier transform, we will obtain the image. We all know that MRI is the greatest invention since sliced bread, and to maintain the analogy, we usually acquire multiple slices through the area of interest. A brain MRI would typically involve the acquisition of probably around 30 5mm thick slices. The acquisition of an MR image involves a combination of RF pulses to tip the net magnetization, various time delays to allow the desired contrast to develop, for example T1 or T2 weighting, and gradient pulses to spatially encode the MR signal. This combination of RF and gradients is known as a pulse sequence. This diagram illustrates the standard method for MRI spatial encoding invented at the University of Aberdeen back in the early 1980s. This method calls the two in-plane directions frequency encoding and phase encoding with the orthogonal slice select direction. An MRI scanner has three orthogonal physical gradients in the X, Y and Z directions, but we will refer to them by their logical names of slice selection, phase encoding and frequency encoding. A magnetic field gradient will not only cause a transient change in the Larmor frequency, but will also induce a phase shift in the transverse magnetization proportional to the strength and duration, that is to say the area of the gradient pulse. This diagram shows three spin vectors that will initially all be processing in phase. I will show the animation in the next slide, but it is important to note how the middle spin will process faster in the presence of the magnetic field gradient, whereas the other two will not. However, at the end of the gradient pulse, all three spins will process at the same frequency, but note that the middle spin will be 180 degrees out of phase compared to the other two. Time is represented by the rolling balls. As the middle ball moves up the gradient, its vector will rotate faster. When the ball comes down the other side, all three vectors will continue to rotate at the Larmor frequency, but the middle vector will have gained a 180 degree phase shift with respect to the other two. So where does K come from when we start talking about K-space? We know from our previous discussions that a gradient pulse, for example along the x-axis, will induce a phase shift delta phi that is equal to the time integral of this gradient pulse multiplied by its position. We can rewrite this equation in terms of a spatial frequency K in units of radians per centimetre, assuming gamma is also in units of radians per second per Tesla. K therefore represents a frequency that changes with position. In the case of a trapezoidal gradient with a constant amplitude, Kx is equal to gamma times Gx times the duration of the plateau, and that the phase shift is simply Kx times the x position. We will discuss this in more detail later. We will start our discussion of spatial localization in MRI with the principles of slice selection. To acquire an axial slice through the brain, we will use the Z gradient as the slice select gradient. The frequency at the center of the slice is given by omega Z, where Z is the distance from the magnet isocenter. Because we need to excite a slice of finite thickness, we need to excite a range of frequencies about this center frequency. The slice profile in frequency space will look like a top hat function. However, we need to create our excitation pulse in the time domain. So the conversion from frequency to time is done via the Fourier transformation, and the Fourier transform of a top hat function is a sinc function. This sinc function envelope is then mixed with the omega Z carrier frequency and played out in the presence of the slice select gradient. Therefore, only nuclei whose precession is resonant with omega Z plus and minus delta omega over 2 will be tipped by the RF pulse. All other nuclei will be unaffected. This shows the RF excitation envelope, which dictates the slice thickness. And here we see that envelope mixed with the carrier frequency, which dictates the slice position. This RF pulse is played out in the presence of the slice select gradient to excite the spins at this desired location and with this desired thickness. The flip angle of the pulse is given by the time integral of the RF envelope. Let us look in a little bit more detail at the RF pulse shape and its associated slice profile. Since a sinc pulse is effectively infinite in duration, it is usually windowed with an appropriate filter to truncate it to an acceptable duration. In this case, we have a 3.2 millisecond Hahn windowed sinc. Sinc pulses are designed in terms of their time bandwidth product, which is equal to the number of zero crossings over the total duration of the pulse. In this case, we have 8 zero crossings. The excitation bandwidth is therefore given by the number of zero crossings divided by the pulse duration, which in this case is 2.5 kilohertz. If we wish to excite a 10 millimeter thick slice, then we would need to play out a slice select gradient amplitude of 0.59 millitesla per meter. Using the Bloch equations, we can then derive the slice profile for this pulse, as you can see on the right. We get a relatively good profile, although the edges are not sharp because we have had to truncate the duration of the pulse. The full width half maximum of the pulse is equal to the desired slice thickness. As we have previously discussed, any gradient will induce a phase, and in the same way the slice select gradient will induce a phase in the spins across the slice. If we take the start of the pulse at the magnetic center, then we gain phase as shown here. In order to eliminate this phase, we need to play out an additional gradient after the slice select pulse with an area which is equal but of opposite polarity. So the area A here must be matched by the area A here. Now we have successfully nutated the spins in our desired slice, we need to spatially encode the MR signal in plane. As we have previously seen, we can do this using magnetic field gradients. And if we express the solution of the Bloch equations for the transverse magnetization in complex notation, and ignoring T2 relaxation for the moment, we have an expression for the signal in the x direction. If instead of the equilibrium magnetization M0, we use the proton density at a particular location x, then the signal is the integral over dx, which is the one-dimensional Fourier transform of the spin density. We can then easily extend this to a two-dimensional distribution of spin density. The proton density distribution can therefore be obtained by a 2D inverse Fourier transformation of the acquired signal data or K-space. We shall now look at the standard method for MRI in-plane spatial encoding that was called spin warp by the inventors at the University of Aberdeen back in the early 1980s. We shall see later the relevance of the warp, sadly entirely unrelated to speed. This method names the two in-plane directions the frequency encoding and the phase encoding. We shall start with frequency encoding, and we use a simple arrangement of 3 tubes of water with slightly different relaxation times to change the signal intensities. Hopefully you will agree that the signal in the frequency encoding direction here represents a one-dimensional projection of the tubes. Following slice selection, all of the spins within the slice will have been tipped into the transverse plane by the RF pulse, so will all be processing at the Larmor frequency. If we work in a frame of reference also rotating at the Larmor frequency, then we can represent the spins at each sample point as a vector that appears stationary. Please ignore the fact that in reality the only signal producing areas would be the bottles, and accept that all the vectors have the same length, i.e. we will ignore all relaxation effects. So following the excitation pulse, the vectors will have 0 phase differences, and therefore we can consider them to be at the center of K-space. If we first apply the positive polarity pre-phasing gradient, circled here, the phase of the spins will move to the far right-hand side edge of K-space. The 180-degree pulse will then flip the phases, so the spins are now positioned at the far left-hand side. We will now turn on the frequency encoding gradient, represented by the blue plane. Here we can see at isocenter, the vectors still appear stationary since we are in the rotating frame of reference, but as we move away from isocenter towards the right, the frequency of precession increases in a positive sense due to the increasing strength of the gradient. Similarly, if we move away from isocenter towards the left, then the frequency of precession increases in a negative sense due to the negative gradient amplitude. Remember that in the laboratory frame, this would just mean that these vectors would be processing slightly slower than the Larmor frequency. We arrange the timings of the gradient pulses such that the frequency encoding gradient, shown here, occurs at the same time as the spin echo is formed and also digitized. The digitized echo, after demodulation to remove the Larmor frequency carrier, would then be stored as a line of K-space, in this case in the center of K-space. The Fourier transform of this echo would then be the one-dimensional projection of the bottles as shown here. This is often known as the central slice theorem. However, we do not have any information as to the positions of the tubes in the other in-plane direction. And this is where phase encoding comes into the process. Just before we talk about phase encoding, here is how we calculate the amplitude and duration of the frequency encoding gradient. Each sample in the frequency encoding direction represents an incremental change in kx. The operator, who controls the scanner, provides the desired number of samples, nx, and the desired receiver bandwidth, in this case plus or minus 16 kHz. Then the pulse sequence can calculate the required gradient amplitude and duration, Ts. To encode the other lines of k-space, we introduce the concept of pseudo-frequencies in the phase encoding direction. The phase encoding gradient, circled here, is applied orthogonal and prior to the frequency encoding gradient, and introduces a phase twist or warp, as we discussed before, into the spins along the y direction. During imaging, the spin-echo pulse sequence is repeated ny times, with the area of the phase encoding gradient being stepped through ny-1 values, spanning a maximum negative area to a maximum positive area. In this first example, again in the rotating frame of reference, the phase encoding gradient pulse is represented by this blue plane. And because this is the maximal phase encoding, what will happen is it will induce a relative pi phase shift between adjacent samples in the y direction. So this can be seen happening dynamically in the movie, and here statically after the phase encoding gradient, where this relative phase shift can clearly be seen. Now, because we apply both the phase encoding and the frequency encoding pre-phasor gradient at the same time, we again move from the center of k-space to the top right-hand corner of k-space. If we then apply a 180-degree refocusing pulse, then those spins flip to the start at the bottom left-hand edge of k-space. So if we now apply the frequency encoding gradient to the spins that have already been warped by the phase encoding gradient, then when we read the spin echo signal out in the presence of the frequency encoding gradient, we will acquire an echo which goes into the bottom of k-space. So we get a line of data located at the bottom of k-space. We will now consider the minimum positive phase encode area. In this example, again in a rotating frame of reference, the phase encoding gradient here with the minimal area is again represented by the blue plane. Because the gradient area is minimal, this will induce a relative 2 pi phase shift across the whole of k-space. This can be seen dynamically in the movie, and here statically after the minimum phase encoding gradient has played out. And again, we can clearly see the relative phase shifts. If we then apply the same frequency encoding pre-phasing gradient, this will move us from the center of k-space along to the edge and very slightly up due to the phase encode gradient. The 180-degree pulse will then flip the spins over to the other side, and then we will play out the frequency encoding gradient again, but this time when we apply out the frequency encoding gradient here, the spins have got this retained phase variation induced by the phase encoding gradient. So this time when the echo forms in the presence of the frequency encoding gradient, we will acquire a line of data which goes just below the center of K-space. Here you can see the range of phase warps that each phase encoding gradient step creates. Unlike the frequency encoding gradient, the important parameter when phase encoding is the area. The maximum area is calculated as shown here, and then that area is divided by the number of phase encoding steps minus 1. Note that we do not usually collect a line of data through the center of K-space, i.e. with 0 phase encoding gradient area applied. Just to make sure the relationship between the RF and gradient pulses is clear, we will go through the K-space trajectory again for a spin echo sequence. The pulse sequence is essentially our sat-nav through K-space. The 90-degree excitation pulse will essentially take us to the center of K-space. For the purposes of this illustration, we do not need to be concerned with the slice select gradient pulses. We then simultaneously apply the maximum phase encoding gradient and the frequency pre-phasing gradient. This will take us to the top right-hand corner of K-space. The 180-degree refocusing pulse will then flip the spins to the bottom corner of K-space, and then we acquire the echo in the presence of the frequency encoding gradient, and this digital echo after demodulation gives us our bottom line of raw data. This is the next repetition. Again, the excitation pulse takes us to the center of K-space. The frequency encoding pre-phasing gradient is the same as the previous acquisition, but now we play out the next phase encoding gradient, which has a slightly smaller area. This time we go to a point in K-space slightly below the previous excitation. The 180-degree pulse then takes us or flips us to a position just above the previously acquired of data, and again when we read out the echo with the same frequency encoding gradient, we get our second line of K-space. The whole process is then repeated KY number of times so that the whole of K-space is filled. And once we have filled all of K-space, then we can perform the 2D inverse Fourier transform to reconstruct the image. This movie shows a real spin echo pulse sequence with 128 phase encoding steps acquired on one of our clinical MRI systems. Note that all the gradients are the same except for the phase encoding gradient circled that is stepped plus or minus 64 times from a maximum negative area through to a maximum positive area. Each echo is then placed in the appropriate point in K-space, and in this example I have performed a Fourier transform of the partially filled K-space as each KY line is acquired. Note that in clinical MRI systems the image is not reconstructed until all of K-space is filled. The pulse sequence diagram shows approximately the first 20 milliseconds of a spin echo sequence. The TE is 12 milliseconds and the TR, to allow for T1 recovery and hence create a T1 weighted image, is 500 milliseconds. Therefore, the total acquisition time for this image is 500 milliseconds times 128 phase encoding steps, which is 64 seconds. This is the spin warp method developed by Jim Hutchinson, just inside the imaging system here, and Bill Ellerstein, shown here, and others at the University of Aberdeen in the 1980s. The team went on to commercialise this system, and it was one of these systems with a field strength of 0.08 millitesla that I started my career in MRI at St Bartholomew's Hospital in London in the mid-1980s. It's probably because of this commercialisation that meant that none of the Aberdeen team were also awarded that 2003 Nobel Prize. One person who certainly did think that they also deserved a share of the prize was Raymond Damadian, who we met in the first lecture, but that's another story altogether. Here is a montage of every fourth K-space and reconstructed image from the movie in the previous slide. Top left here is the first line of K-space, with the rest of K-space just filled with zeros. Following inverse Fourier transform, the image simply shows a one-dimensional projection. As we acquire more K-space data, the images start to show the edge of the head, or the high spatial frequencies. As we pass just through the center of K-space, then we start to see the brain, as we are now sampling the low spatial frequencies, which represent the bulk of the contrast in the image. Note that as we acquire the bottom half of K-space, all we are doing is simply improving the spatial resolution in the images. Here are a few observations about the inverse relationship between K-space and the reconstructed image space. Firstly, note that the extent of K-space is inversely related to the pixel size in the image, and the spacing between individual samples is inversely related to the field of view in the reconstructed image. For example, if we wish to increase the field of view but maintain the same number of samples, then the K-space sampling interval needs to become smaller. This will reduce the overall extent of K-space, so the pixel size will therefore become larger. Similarly, if we want to make the pixel size smaller to improve our spatial resolution, then we need to increase the extent of K-space for the same number of samples. This will increase the K-space sampling interval, and therefore the field of view will decrease. To illustrate this point here, I'm going to increase the matrix from 256 by 256 squared to 512 by 512 squared, so that the extent of K-space is doubled in both directions. But the sampling interval is the same, so the field of view is unchanged, in this case 256 by 256 millimeters. The image on the right has a better spatial resolution compared to the one on the left, and if I just zoom the one on the left up by a factor of 2, then if we look particularly at these resolution holes, we can see the better spatial resolution on the image acquired at 512 by 512 compared to the image acquired at 256 by 256. Another interesting feature of K-space is that it has Hermitian symmetry. So the grey region is the complex conjugate of the coloured region. This means that we can use techniques such as partial Fourier acquisitions, where we only acquire the red samples, thereby reducing the overall acquisition time, but by virtue of this symmetry, we can synthesize an approximation to the missing yellow data here. The result is an image with a full spatial resolution, but a decreased signal to noise ratio because we've reduced the number of KY samples. Alternatively, we can acquire partial echo data in the KX direction. In this application, we reduce the amplitude of the frequency pre-phasing gradient in this gradient echo readout, so that the echo does not form in the center of the frequency encoding gradient, but slightly earlier in time. We then sample the red data points again and use Hermitian symmetry to synthesize the yellow points. This technique is often used when we need to shorten our effective echo time here. The dimensions of reconstructed MR images is usually a power of 2, for example 256 or 512. This is because there is a special variant of the Fourier transform which is extremely time efficient called the fast Fourier transform, which requires the input data to be a power of 2. In a typical MRI system, if we acquire a non-power of 2 matrix such as 288 by 288, then the raw data will be 0 padded to the next biggest power of 2, 512 by 512. Following reconstruction, we will then get a 512 by 512 image, but we are in fact sync interpolating the data. So the acquired pixel size here will be 240 millimeters divided by 288, giving a resolution of 0.83 millimeters. But the interpolated resolution will be 240 millimeters divided by 512, or 0.47 millimeter. The use of acquired or interpolated pixel size needs to be considered very carefully when making measurements from MRI images. MRI scans are quite long because of the need for a relatively long TR, with generally only one phase encoding step being acquired per TR. But this does mean that for most of the TR, nothing is happening except T1 relaxation in order to give us the desired contrast. To make MRI more efficient, we interleave other slices during this TR period. This simple example shows 3 slices being interleaved in the TR period. All that is going to change between slices is the carrier frequency for that slice location. The RF envelopes will not change since that only dictates the slice thickness, and that will be the same for each slice. Since only the carrier frequencies are different, only the spins within each slice will be excited and all the other slices will recover normally. In a T1 weighted scan with a TR of around 500 milliseconds, we could fit approximately 30 slices into the TR. So although it's going to take several minutes to acquire the data, it does mean that we will acquire 30 slices during that time period. A modification of the spin echo is the inversion recovery sequence. This starts with a 180-degree inversion pulse, which inverts the net magnetization from being along the positive z-axis to the negative z-axis. We then wait a time from the end of that pulse to the excitation pulse of the spin echo sequence. This time is known as the inversion time, during which the magnetization will recover due to T1 relaxation. The recovered magnetization will then be detected in the transverse plane using the spin echo sequence. Here we can see the inversion recovery curves for CSF, grey matter and white matter. In this example, we are making use of the real component of the complex data because it encodes the polarity of the magnetization. The grayscale now goes from negative to positive. Real, or sometimes called phase-sensitive inversion recovery images, are characterized by the fact that the background air with zero signal is displayed as mid-gray. This is an example that's been acquired with an inversion time of about 160 milliseconds. So even though the signal is all negative, CSF appears darkest, with the white matter appearing brighter than the grey matter, exactly as would be expected from their relative T1 relaxation times. What happens if we take the magnitude of the data rather than the real component? Well, everything that was negative simply becomes a positive value, and the signal recovery curves look like this. So now, for the same 160 millisecond inversion time, we can now see that the CSF is brightest, followed by grey matter, followed by white matter. This slightly strange contrast has some applications, particularly in the fact that you can see that for certain inversion times, the signal for different tissues actually hits 0. So with a careful choice of inversion time, we could actually null the signal from any tissue based on a knowledge of its T1 relaxation time. One application of magnitude reconstructed inversion recovery is the so-called short tau inversion recovery, or STIR sequence, where tau was the original name for the inversion time. This is an application for the suppression of fat in an image. Fat is often a confounding feature because it has a very short T1 relaxation time and therefore appears very bright in T1 weighted images. This diagram shows the magnitude recovery curves for fat and also for water. Note that because of the short T1, the fat signal reaches 0 at approximately 180 milliseconds inversion time. Images that are acquired using this technique, such as the ankle here, demonstrate very good fat suppression, particularly including the bone marrow. In this patient, there is also some fluid accumulations at the bottom of the foot, and because the T1 of fluid is long, in the magnitude reconstruction, the fluid appears very bright and may add to the clinical diagnosis in this particular patient. If you happen to know the T1 of a particular tissue, then the Ti to null that tissue is simply given by the natural log of 2 multiplied by the T1. Here is an example of using inversion recovery magnitude data to null the signal from cerebrospinal fluid in the brain. This is known as the fluid attenuated inversion recovery, or FLAIR sequence, where we use a TI of approximately 2.7 seconds to get this null point. Since this is a T2 weighted brain image, we would have expected the CSF signal in the ventricle to appear very bright. However, due to this inversion recovery preparation, the CSF signal is suppressed, and therefore we can now clearly see these periventricular white matter changes. Here is a comparison of an axial T2 weighted brain image acquired without and with the FLAIR inversion pulse. The small white signal hyperintensities arrowed here on the FLAIR image would be extremely difficult to identify on the conventional T2 weighted image because of the high signal from the CSF. The last pulse sequence I want to briefly explain is the gradient recalled echo sequence. In comparison to the spin echo sequence, a gradient echo sequence does not use a 180-degree refocusing pulse. Instead, the echo is formed by making the frequency encoding prephasing gradient negative, which forcibly dephases the transverse magnetization, and then making the frequency encoding gradient the opposite polarity, which forcibly rephases the magnetization, forming what is known as a gradient echo. Since we are not using this 180-degree refocusing pulse, the gradient echo cannot eliminate the effects of T2 prime. Therefore, the image is weighted by T2 star decay. The use of T2 star weighting is often useful in certain pathologies, such as in this patient who has had a brain bleed or a hemorrhage, and the dark outline here is due to a rim of hemosiderin, which is a breakdown or a byproduct of the breakdown of red blood cells. This image also shows signal loss at the front of the brain. This is due to the presence of air in the sinuses below this slice. The difference in magnetic susceptibilities between tissue and air also causes T2 prime dephasing, resulting in this signal loss. Gradient echo sequences also often use excitation flip angles which are less than 90 degrees. This means that they can be operated with very short repetition times without substantially saturating the longitudinal magnetization. This slide compares the gradient echo pulse sequence with the spin echo. As already discussed, the gradient echo uses a gradient reversal to form the echo, whilst the spin echo uses a 180 degree refocusing pulse. The gradient echo forms under the T2 star decay curve, whereas the spin echo forms under the T2 decay curve. The gradient echo sequence typically uses a flip angle less than 90 degrees, so the signal equation is somewhat more complicated, involving not only TE and TR, but also the flip angle alpha. Whereas the spin echo sequence has a relatively straightforward signal equation. Note that there are a number of variants of the gradient echo sequence that have quite different image contrast appearances. The image here is obtained using a T1 weighted, or sometimes called spoiled, gradient echo sequence. Here I also show a T1 weighted spin echo image for comparison. This is the image that I showed you previously, with this region of signal loss here due to air tissue susceptibility and this dark ring of hemosiderin. The same slice acquired with a spin echo sequence, we can see that because we've eliminated T2 prime, we no longer have any signal loss in this frontal region here, and we also do not see that black rim of T2 prime dephasing here. One advantage of gradient echo imaging is that with a short enough TR, we can acquire true three-dimensional or volumetric imaging. In the case of three-dimensional acquisitions, we acquire a second phase encoding gradient, but this time applied along the slice select direction. The slice select gradient, first of all, excites a large slab of tissue, and then this slice encoding gradient divides that tissue up into contiguous slices. So the two phase encoding gradients together with the frequency encoding gradient encodes a three-dimensional K-space. The images are then reconstructed using a 3D fast Fourier transform. A short TR is required because the acquisition time is going to now be given by the TR multiplied by the number of in-plane phase encoding steps multiplied by the number of through-plane or slab encoding steps, and also multiplied by any signal averaging that we may care to do. The advantage of volumetric imaging like this is that very thin slices, typically 0.7 millimeters or less, can be reconstructed, and therefore we can end up with isotropic voxels that can then be reformatted into any plane. The last topic I want to talk about briefly is fat. Fat can be a confounder in MRI. The main constituent of body fat in humans are triglycerides, which are relatively large molecules containing lots of CH2 or methylene groups. Because of their large structure, the electrons partially shield the protons from the static magnetic field, which means that the protons in fat process a slightly lower Larmor frequency, which can be seen in this spectrum of fat, where the methylene resonance is about 3.4 parts per million lower than water. This is approximately 220 Hz at 1.5 Tesla. If you also think back to when we discussed molecular tumbling, large molecules like triglycerides that tumble near the Larmor frequency demonstrate more efficient T1 relaxation and hence have a shorter T1. So that's the reason why fat appears hyper-intense on T1 weighted imaging. A consequence of this difference in precessional frequency between fat and water means that in gradient echo imaging, the fat and water signals will have a different relative phase with each other depending on the echo time. By careful selection of the TE, it is possible to obtain images when the fat and water happen to be in phase, such as now, or when fat and water are out of phase, as is the situation now. In the outer phase images, i.e. those that have been acquired with the echo time equal to the outer phase TE, you will see a black line surrounding tissues where the voxels contain an equal admixture of water and fat, resulting in signal cancellation. Obviously, we do not see that appearance when we've acquired images at the in-phase echo time. We can make use of this difference in precessional frequencies to suppress or saturate the signal from fat if we do not want it in our image. One common method is to use a chemical shift selective or CHES fat saturation pulse prior to the imaging sequence. Here we can see the peaks for water and fat, with fat approximately 220 Hz lower. If we apply a frequency selective pulse centered on the fat frequency, then we can saturate the signal from fat by tipping it into the transverse plane and then using a magnetic field gradient pulse to dephase the signal before we play out our spin echo imaging sequence. So a simple 7 millisecond duration RF pulse will excite this relatively narrow bandwidth of approximately 150 Hz. If the pulse is centered on fat, then it will have little impact on the water peak. Here are two T1 weighted images acquired without and with this CHES fat suppression. The fat saturated pulse does a reasonably good job of suppressing all the intra-abdominal fat. This is the white signal, the very bright signal here, which is quite well suppressed. There are small fat saturation failures at the bottom of the images. This is due to the uniformity of the static magnetic field, and at these extreme regions the Larmor frequency of fat has now shifted outside the bandwidth of the fat saturation pulse. Finally, we saw this case earlier on when talking about STIR, where the fat is suppressed based on the T1 relaxation time. Here we compare STIR with a T2 weighted image using the chemical shift selective fat saturation method. Because the ankle is a very difficult area to obtain a very uniform static magnetic field, we can see clear non-uniformity of the fat saturation in this image. In comparison, the STIR method does a much better job. So this is the end of the second lecture, and hopefully now that you feel that you should be able to explain the principles of MR image formation and also describe the spin echo and gradient echo pulse sequences. So thank you very much, and I look forward to talking to you on the third and final lecture.